Alright, I know some of y'all are still doing the bell ringer or still cutting things out, so to give you a little bit more time to finish doing that, one, try to get the bell ringer done while I do Mathematician Monday, but two, make sure you get those cards cut out because we're going to use them in a little bit. But today is all about equivalence with linear, exponential, and quadratic functions. P.S. I'm going to pass back the linear and exponential demonstrated understanding later. We're going to talk about a couple of small details. Overall, it's a really strong start for your first demonstrated understanding. But I just want to go over a couple of details that I noticed with y'all, especially the backside graphing and making the table, and improve your understanding and do better next time. Because we are going to have a demonstrated understanding on just identifying the linear, exponential, or quadratic in each of the different forms tomorrow, but there will also be a little bit of linear and exponential on there. Just kidding. I said Wednesday. Don't lie to me, babe. I said Wednesday. Thanks. So, yeah, we'll get to that. But today we're going to do this lesson 3 samesies from the textbook. Hopefully we'll get into more about quadratics. I know some of y'all are like, Mr. Kenny, I need more practice with the quadratics. Yeah. The quadratics is what we're going to spend about a week on at this point. We'll do a little bit with linear and exponential to build y'all up. But the quadratics is the main portion of our unit at this point, specifically looking at the 3 different forms of a quadratic, okay? But that's really starting at the end of today, or not tomorrow, I guess, on Wednesday. All right, Mathematician Monday, though. Bob Moses, man, I had heard of this, well, I've heard of a project of this guy once upon a time, but I had not looked into the life of him until last night when I was trying to figure out what Mathematician Monday I wanted to do. Absolutely wild life, someone that we should definitely look to. So first off, Bob Moses, I think probably the first Mathematician Monday that we're looking at that doesn't have a PhD, but weirdly enough, he also doesn't have any kind of degree in mathematics whatsoever. He was actually born in Harlem, 1935, to a dad who was a janitor, mom who was just a homemaker. So definitely one of those cases where it's like, man, that guy came from nothing. But his story is absolutely wild to me. So, studied philosophy and French, definitely not math, right? In college. He went on to get a master's in philosophy, still not math, from Harvard. And he started a PhD in philosophy, I don't remember which college, but he started one, and then his mom passed away, his dad got sick, and so he quit that. But when he quit that, he went in, he went home and he started teaching mathematics. And so when he started teaching math in the Bronx, that was right around late 50s, early 60s, and he became very well acquainted with the civil rights movement in New York because he saw people, college students, protesting and around New York City. And so he actually became very heavily involved in the civil rights movement and moved to Mississippi. I don't know how you go from New York City to Mississippi, but he did. And so he went to Mississippi in '61, started pushing back on the disenfranchisement of black adults who could vote but were not being allowed to vote for various reasons, right? So if you look into the Jim Crow laws and all those issues, then you know more about that. But I'm going to get into the math side of it, right? So obviously teaching math, that's what he was. So he was a mathematician, but not in a traditional sense, not trained in any kind of degree or anything like that. Still came from nothing, which is just a story to look forward at. But one of the things that I love about Bob Moses that I was surprised by was in 1964, there were 3 volunteers that were murdered in Mississippi. James Chaney, a young black man, Andrew Goodman, and Michael Schwinner, who were both Jewish men who came down from New York City to support the civil rights movement. And in the face of these murders, he is a guy who actually held everybody together through nonviolence. He pointed out that if we want to make a difference, fighting and violent approaches is not the way to make that difference, very similar to what MLK did in Alabama with his stuff. But he was all about making a difference in the civil rights movement, which takes me into the second half of this, right? So he went to Tanzania, he protested the draft by leaving the country. He, one, was not within the age range. He was actually too old to be drafted, yet he thinks there's some political shenanigans that happened. And so when he came back, he actually was granted a MacArthur grant, which, if you ever look into that, one, you can never nominate yourself, like someone else has to nominate you, believing that what you're doing can make a difference in the world, and he won. Like, it's one of the hardest things to win. He won it, so he started this thing called the Algebra Project to improve minority education and math literacy. So this is a couple of things that I thought were amazing. He saw advancement in math literacy as the next phase of civil rights struggle. And this quote from him in 2013 absolutely blew me away, where he said, education is still basically Jim Crow as far as the kids who are in the bottom economic strata of the country. That's not 60s, it's not the 70s, it's not the 80s, that's in 2013. He made this statement, and I don't know how much I've talked about it, but like my undergrad's in civil engineering. The reason why I became a teacher is because I saw the same issues. Like I want to make a difference, like, in education matters. And so I'm going to do things differently because I don't want education to continue to be the Jim Crow of our country, right? So I'm going to be different, but I promise you it's because I care about you, because I want to change that system. And so he saw algebra as a critical gatekeeper because it was really hard to go to college without it. And this is the reason I'm really celebrating him. Well, just one, civil rights stuff is amazing, but right here in Mississippi with the Algebra Project, he took the students who scored the lowest on state math test in middle school, and over high school, they did extra work with those specific group of students. And with that specific group of students, their proficiency was almost 50% over those on the standard curriculum, right? So they took the lowest scores, and I think the people on the standard curriculum at the end of high school were scoring about 40% proficiency on the exit exam, whereas the students in his program who were taking extra math, doubling up and getting extra practice, were scoring 55 to 60%. And so, one, absolute visionary, trying to change the way that we think about education, the way things work, but what he also recognized, and what I want to emphasize and celebrate, is hard work pays off. He made sure that he was putting in the time and effort, and I think that we as educators need to change maybe the way we're doing things at times, providing more support to students, but the students who scored the lowest ended up being way above the people in the standard curriculum who started out higher. Because at the end of the day, hard work pays off. And so he was there to support them. And so Bob Moses, absolutely phenomenal guy. You can look more into his history, especially the stuff he did in civil rights. It was wild. But now on to our algebra to make sure that we make a difference in the world of education for us. So actually, I want to do the bell ringer before we look at the proficiency scales. So bell ringer, please pay attention to these questions, even if you didn't get a chance to do them, because I'm going to cover a couple of really important details that I need us to recognize. The most common response here was that this is 5x plus 2y. I see some people didn't do anything with the 6y minus 4y, but let's talk about this because we also have x to the 5th plus 6y minus 4y. So what's the difference between these two responses here? Okay, so notice there's 5x's here, right, with an exponent, but what are we doing with an exponent? Repeatedly multiplying, right? That's why an exponential function has repeated, not just repeated, but constant. For exponential, constant multiplication, right? repeatedly multiplying by the same amount every time. So why is it 5x?
Because you're adding all the x's together.
I'm repeatedly adding x how many times? 5 times, right? So 5 times x, that multiplication is repeated addition, right? And then so why is 6y minus 4y actually 2y?
Because negative 4y.
Because what? Yes, I need a little bit more detail with it. No. What do you think, Jaden?
Negative 4.
Yeah, but why does 6y minus 4y come out to be 2y?
Because if you reverse it, like 4 plus 2, that equals 6.
Yeah, but y'all are completely ignoring the idea of the y's, aren't you? Why is 6y minus 4y 2y?
Because 6 minus 4 is 2.
But then you're completely ignoring the y's. Yeah, so why does the same variable matter?
Because they can be combined or like subtract or separate.
They can be. Why can they be combined? Why can they be added and subtracted? Woo! Alright guys, I talked about this once. I know it's been only once, but we need to pay attention to this detail because this is going to impact our understanding and ability to work with exponents as well. What is multiplication actually? Repeated addition. So when I say 6y, what am I really saying? See, this is why I need to be careful. I have 6y's being what? Added together. What am I doing to those 6y's? I'm taking away 4y's. I want to formalize, and I want to make sure this is clear because it's not 6 minus 4. It is 6y's minus 4y's, which leaves me with how many y's? I'm literally left with how many y's? 2 being added, right? It's not just like the idea of they have the same variable because the power matters as well. Can I do 6x squared plus 2x? Actually, let's make this easier because I'm going to do something. Can I do 3x squared plus 2x? Why not? Because why? Hey guys, what does 3x squared really mean? What does 3x squared really mean? Adding x squared how many times? 3 times. So if I add 2x to that, are those the same thing? Okay. Like it's important to understand these different terms. By the way, I would call this a quadratic term, and I would call this a linear term. Does anyone know why I'm calling this quadratic and this linear? Anyone see anything here that might make us think quadratic? Not just any old exponent. An x squared, a second degree exponent, right? So why would this be linear here? Not just variable. When I write the equation of a line, what's the understood power on that x? What's the understood power on these x's? So quadratic because it's x squared, linear because it's x to the first. Okay? So I want to make sure that language is clear. That might be something I need to add later on proficiency scales. But guys, it's not random. It's important to understand this idea of repeatedly adding and subtracting things. Whereas like here, these are x squareds and these are x's and they're not the same thing. It's not just, hey, like terms. What do we mean by like terms? X squared and x are different quantities, so I can't add and subtract those different quantities. Does that make some sense? Questions about those details? Whereas, I'm going to contrast that very clearly here. Okay? So, in this one, a lot of us, so I have a 5 to the x. I have a lot of x to the fifths. So, Is it 5 to the x or x to the 5th?
X to the 5th,
And for each of them,
Why is it x to the 5th?
but just constant multiplication.
It's constantly multiplying what? Oh, is it only 5x's and I drew 6, I think? So we're multiplying x 5 times, right? So x to the 5th. 5 to the x, don't forget, that means I'm multiplying by 5. How many times? 5 to the x? Yeah, we don't know, right? Like, when I say 5 to the x, I don't know how many times I'm multiplying by 5. So be careful with that, right? 5 to the x means I'm multiplying by 5, and I don't know how many times. X to the 5th is that. Now, I have one person who said x to the 5th times y squared. Anyone else for the, actually I got kind of, that just is a miss, right? Most of us left as y to the 6th divided by y to the 4th. Where does the y squared come from? Because I will agree, that is correct.
From the 4 and y to 5.
So I'm going to hit on what Miles is saying in a second. He said something about cancellation. I want us to think about that. Can you explain a little bit more, Jaden?
I was going to say y to the 6th power is getting subtracted by y to the 4th because of
Okay.
division.
Very close, just a little bit on the language. What's actually being subtracted? The y's. The exponents, right? 6 minus 4. Okay? Because what's happening to the y to the 6th and the y to the 4th? And that's where I'm going to push on your language a little bit, Jaden. What's happening to these terms? They're being divided, right? They're divided, which is going to cause us to subtract the exponents. Does anyone know why we're going to subtract those exponents, though?
Because division is the opposite of multiplication.
Close. It is connected with that. It comes back over to here. This is why I'm emphasizing this so heavily. 6y means I'm repeatedly what? What am I repeatedly doing? Adding y how many times? 6 times, right? Then I'm taking away 4 y's, right? So I had 6 y's, I'm taking away 4 y's. So what's happening over here? What do we mean when we say y to the 6th divided by y to the 4th? That exponent's repeated what? The exponent's what? Multiplication. So y to the 6th means I have y times y. And then what am I doing to those 6 y's that are being multiplied? Ish. Yes, in a second, but what am I doing? I am dividing by how many y's? Kristen, what's y divided by y? You say y?
Yeah.
What's 5 divided by 5?
1.
What's 17 divided by 17?
1.
So what's y divided by y?
1.
There we go. Right? Peyton, what's y divided by y? Y divided by y? 1, okay. Landon, next y divided by y? 1. Sarah, next y divided by y? Okay. Then notice how many y's am I left with? 2. So why is it y squared? Well, because that multiplication is repeated, or the exponent's repeated multiplication, and I'm dividing by 4 y's. And so I'm taking away those 4 y's, which I think is what you were saying canceling earlier, and that's what I was going to point out, right? We are canceling because division is the inverse of multiplication. Okay? So there's these properties and these rules, but they're not random. I want us to understand what's happening with these exponents, right? So we're locked in, right, Davis? I'm not wasting my breath. We understand better? Okay? These exponent rules and the idea of adding and subtracting like terms are really important. Please hold on to these because it's going to make some of the confusion later easier. Especially when I'm going to talk about linear and exponential once we get you back here demonstrating understandings. All right, last couple details. Y equals 7 minus 3/2 to the x plus 4 squared. Most common response that I got was that this is exponential. Y'all still think exponential? I got no linears. Why no linears? Leah, what'd you put?
I put
Okay, so why are you thinking quadratic? Because what?
because of the two.
Because of the 2? Because of that 2?
No.
The exponent that's a 2? Anybody want to push back on that or add on to that? And I can look in a second who put exponential. I can call on y'all. Anybody want to push back on it? Or do we want to change our mind? You see why she said it? Okay, so let me ask you this, Leah, why didn't you say exponential?
I was thinking about like the way it was like set up. You know, like an exponential is like a. I was thinking how it's usually set up. It's supposed to be set up, and it worked.
So what's the issue with this one versus this traditional exponential? I want to emphasize this, right? I need y'all to pay attention to this. I can very easily rewrite this, one small detail different. Notice there's a lot of similarity here, but why is this one exponential?
Because x is the exponent.
Because x is the exponent. I need y'all to pay attention to that and recognize that. It's only exponential when the variable is an exponent, because that variable exponent indicates that I'm repeatedly what? By? Yeah, what number in this case? 4. And do we know how many times it could be multiplied by 4? No, right? That's the idea of exponential. We're repeatedly multiplying, we don't know how many times. But here we got a square, so it is quadratic. We go with that idea? Now I want to compare that against the very next one, which I think was almost identical, wasn't it? But it was set up this way. So what's the difference here? Most of us said linear in this case. So why is this one linear, but this one was quadratic? This is and by the way, I'm doing this because this is a commonly missed question on my assessments. Not doing this for kicks and giggles. Why is this one linear and not quadratic? Looks a little weird, doesn't it? Guys, I get it's Monday. Come on, don't blankly stare at me though. We gotta get to a new lesson. Why is this one linear? Okay, so first off, there's no exponents, right? So that should make me think linear. Is there a reason why we were thinking I don't think it's linear, or we weren't sure what it was? So I only got, what, 10 of us who said linear? Why were some of us unsure about it being linear? I'm trying to open the floor to give some of you a confusion, a chance to ask a question. I can't answer questions that are not asked. Okay. My assumption was, and I am not answering questions that are not asked in the future. My assumption is most students are like, well, Mr. Kenny, the linear equation is y equals mx plus b. And then does that look like y equals mx plus b? It can, but does it right now? No. Notice, remember, linear has multiplication indicating repeated what? Repeated addition. The highest power is a first power. Notice the highest power on the x is to the first. It's actually something known as a point slope form of a line, or a version of it, but this is slope intercept. But you can distribute here. You can't distribute up here, we'll talk about that why later, but you can distribute in this case. And this would come out to be 6. 7 minus 6 is 1. Does that now look like a linear? So even though these looked different, what are they actually? The same. Oh, come on, even more mathematical term than that. Equivalent, right? They look different, but if I graph both of them, they're going to map to each other. The same inputs map to the same outputs. They are what again? Equivalent. So remember, this multiplication, simple multiplication, is repeated addition. This square up here, though, will happen before the multiplication. So don't forget your exponent rules, or your order of operations. Exponents happen before multiplication. That's why I can't distribute here, because I'd have to do the square first. And that square is forcing it to be quadratic. Hopefully that helps us have a recap of some linear, exponential, and quadratic ideas. What are your questions at this point? Going once? Going twice? Bella?
How did the X and then the
So, from this point you're talking about? Like that? So, one property of algebra is known, or just numbers, is known as a commutative property. And so like 5 minus 3, that's the same thing as negative 3 plus 5, right? I just switched the order. And so the same thing is true here. I can switch this order, I just gotta make sure I keep my signs correct. So that's negative 3 halves, that's a positive 7. And then that positive 7 minus 6 is 1. That's known as a commutative property. As long as you're staying as a single expression on the same side of the equation, you can switch the order of adding and subtracting. There's also a commutative property for multiplication, right? Not for division, not really, kind of for subtraction, but multiplication and addition is pretty easy. That makes sense? Thank you for that good question. Dang it, that's what I meant to grab yesterday. I'm gonna fix that. I have to go to my Publix. Sorry, background. I'm gonna go grab some Starburst, and when I have really good questions, I'm gonna start like tossing out some Starburst, because I need y'all talking more and asking more questions. Doesn't mean every question gets a Starburst, but really good question does. You can see Crystal's really excited about that. You don't get any Starburst. Alright, moving on. Oh gosh, not even like a half smile or anything. I can't tell if it was just that bad of a joke or just we're not in the mood for jokes.
Monday morning.
It's Monday morning. Alright, but we gotta get moving. We do have practice ACT tomorrow, and so we gotta get through some stuff today. So, I want to point this out. If you are looking at yellow proficiency identifying functions, have we looked at determining if a relation is a function? Dog. Have we figured out how to determine if a relation is a function? Yes. Have we talked about identifying the type of mathematical representation? Yes. Relations, functions, mathematical representations, those are key terms that we have got to know. Have we looked at determining if a relation is linear, exponential, or quadratic? Notice we have now finally added in those quadratics, right? So we have actually hit everything on this proficiency scale now. That's why we're going to have a demonstrated understanding on identifying those functions tomorrow. We're going to talk about some more details later, but we already have hit on two of the major ones. How do we know if we have a quadratic in an equation? Oh, we just talked about it. Yeah, as part of the bell ringer. How do we know that one was a quadratic? What? Was it? What about that two? What? And what exponent? Square, right? An exponent to the second power. That's quadratic. How do I know, Crystal, if I have a quadratic as a graph? There we go, right? We see that parabola, whether it's concave up or concave down, we got a quadratic, thank you. Woohoo! Yeah. So I just wanted us to get to that point where we're talking about quadratics, right? Yeah, if you have a parabola, obviously you have a parabola, but if you have a parabola as a graph, it is quadratic. Okay? That was the practice that I gave y'all before the demonstration. Alright, next, remember we have done everything with constant rates of change. If I talk about a constant rate of change, what type of function am I referring to? There's two options. Linear or exponential, right? Linear, constant, additive rate of change, whereas that exponential has a constant multiplicative rate of change. We're going to look at your demonstrated understanding a little bit later, but everything here we have discussed. Right, we've got to know how to graph, create tables, write equations, so you can get a little bit more practice of that tomorrow. So don't forget, you also have these Ferrari models with the answers on the back, right? So linear versus exponential with tables, And then down here I have you creating a table from two equations. And then graphically, and then creating a graph from an equation, right? So the idea is very much mild, medium, spicy. Practice those problems, come in and ask questions. We also had that whole practice sheet that I gave you answers for. Work through those. I think, yeah, I meant to do this yesterday. One thing I'm going to do during my planning today is I'm actually going to do a quick, either today during planning or this afternoon, I'm going to do a quick video using Zoom where I record myself talking and explaining as I work through some of those problems from the practice. That way if you're struggling a little bit with those equations and you're trying to work on it outside of class, I'll upload it to YouTube and you can see me actively working through problems and writing out with that explanation. So if that's something you're having trouble with, we will answer questions in class. By the way, you could have asked a question at the beginning of class, but that'll be an option. Whew. To today's lesson, samesies. Graphing or comparing multiple representations of functions, right? So key terms, relation, function, function notation. We've already hit on a lot of that, but I need you to turn to, I thought I put it on this page, but I guess not. It's the like second or third page in here. Page 33. Right? So page 33, in 1-33. Alright? This is the whole reason I had you cut those pages out. So, as a quick reminder, right, we have these definitions here, so take advantage of these. What is a relation? What's a relation?
A method, something that relates.
So being specific and precise with our language, it's a mapping between a set of input values and a set of output values. Davian, how can I represent that mapping of inputs to outputs again? Do you remember how I can represent a mapping of inputs to outputs? Not sure? A table? Can that show inputs and outputs? Okay, what else can show mapping of inputs to outputs? A graph. Anything else?
Algebra.
Algebra, right? Equations, inequalities, expressions. Anything else? Pictures? Anything else? Words. I just want to reemphasize and remind you, like, when we talk about these mappings, and I say, hey, what can represent? That's mathematical representations, right? So when we talk about representing things, we're talking about mathematical representations. That function, though, is a special relation such that, and it says each element of the domain, there exists exactly one element in the range. When they say each element in the domain, anybody know a different way that we can say that? What are the elements of the domain? Well, how have we always talked about functions? Every input maps to one and only one output. So what's the elements of the domain also called? Inputs, right? So when we talk about domain, hold on to that because we're going to talk about that in like 2 units, right? When we talk about domain, that's my inputs, right? The domain is the set of all inputs. And then it says each element in the domain, the inputs, there exists exactly one element in the range, which will be my outputs, right? Each input maps to one and only one output. That's just a different way to define it, but it's the same exact idea. So this is why that language is important, and we need to understand those connections, right? Domain is inputs, range is outputs. Range is outputs, yep. Okay? So, function notation, just please, 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 and I don't think anyone's done this or will, please don't ever call this f times x. How do we read this? F of x, meaning x is my input, f of x is the output. What's another variable we can use in the place of f of x? Variable that we can use in the place of f of x. Something that's equivalent to. Yeah, variable. What's another variable we can use for an output? Say again? Y, right? When we say f of x, that's equivalent to y. Say again. Not, okay, so be careful. So we can actually have that. I'm glad you said that. F of y, in this case, Mr. Hobby, in this case, what's my input?
Why?
Input is now y. So you know what the output would be? This f of y would be the output of x, yeah. We're going to talk about that when we get to inverse functions. This is why it's important to understand this notation, right? The input is literally what is inside the parentheses. It's what you're going to be substituting in, right? And then the output is the other one. So it's very rare that we would do this until later, but you can do something like this, right? In this case, f of y would equal 3y minus 4. Notice y is my input, x is my output. That's where inverse functions are important. So I'm glad you said that, thank you. It's an awesome mistake. And I want to say it that way because I want us to celebrate mistakes. They're great to make. All right, moving on though. So you already have your relations cut out at the end of the lesson. You're going to analyze each relation and then create groups of equivalent relations. All relations have at least one match. And so what I want you to do is when we go to vertical surfaces in a second, you only need one set of cards out because if you use all three, it can get really messy. So you decide whose set of cards you want to use. And if you want to, can I borrow these, Miles? Thanks. What I might do is I might sort, like stand around your desk, sort, right? So maybe I'm like, oh, I think A and B go together, and I think like C and G go together, and then J and H. Oh, or G and K. Oh, H goes with those two, right? So I'm sorting them into groups. Everything has at least one match, but I will go ahead and tell you there's at least one set that has a total of 5 cards, right? So the minimum in every set is how many? 2, the maximum is 5. And what are you trying to find? You're trying to figure out which ones are not just alike, not they're what? Equivalent. And they're actually just relations. There are some, so be on the lookout. There are some that are not functions. But I want you to find the equivalent relations. Okay? You have all the resources at your disposal. You can think about your mathematical representations. You can use your calculators. You can use each other's brains. But I want us to find those equivalent relations. What are your questions? Okay? I want you sorting these things out, and then I want you to write your final answers on the boards so that we can compare and contrast them, right? So write your groupings together. What I will say, now I'll just let you write them however you want. So write your groupings together, okay? Sound good? All right, and go. Okay, but how do we know when they're equivalent? How do we know when they tell the same story? Same inputs, map to the same outputs. It doesn't matter whether it's an equation, whether it's a table, whether it's a verbal representation, a graph. If they're equivalent, the same inputs map to the same outputs. And there's lots of ways to check it. I'm going to talk through a couple of these in a second. So A, which relations did we see that went with A? J and M, anything else? F, I see F over there. So I had F as well. I had G, ooh, I had another one that y'all missed. I didn't get that far. J and M. So let's talk about this one, okay? 2 things that I want us to look at with this. First off, a lot of y'all really notice that line of symmetry. I love that, right? So if I look at this line of symmetry, it's x equals -3. Now, has anyone else in this classroom ever struggled with whether a vertical line is x equals or a horizontal line is y equals? Okay, Mr. Hobby is with me, right? Did y'all ever struggle with that? You just memorized it, moved on? Oh my gosh. Does anyone know why that's the case? Have we ever thought about it? Have we ever thought to ask that question?
No.
Oh man, ask all the questions. Guys, watch this really quickly. Hey, what's this point right here? Guys, we need to be careful with our x and y's. This caused several of us some trouble. -3, 1. What's this point right here? What's this point right here? Oh, technically that's actually a 2 because it's scaled that way. This is... Does anyone see anything interesting about this line here? Well, it's always -3. Wait, the x is always -3? That's why it's a vertical line, because what is the x every single time? Doesn't matter what y is, the x is. That's why a vertical line is x equals. In the same way, if you look at a horizontal line, it's y equals, because the y is always the same. All right, so we need to talk through some of these, but there's that line of symmetry. We can very clearly see if I take this table and I graph these points, the same inputs map to the same outputs. But let's start looking at the equations, because a lot of us had J, A, F, and M, but we missed this one. Okay. First off, the next lesson we do is we're going to focus on the different types of equations. Okay. But Miles, talk to me about what you did earlier with a similar problem when it was written like this.
Like how I solved it. Or just.
Be careful that word solve. Solve means to find what makes the equation true, but maybe figured it out. Figured out the problem. Figured out an equivalent representation.
I don't know, it's kind of like remember old math.
Remembering old math?
Yeah. And I just went like x and x3 and 3x and 3.
Anyone know what Miles is talking about there? Don't you say that word in my classroom.
We should fold.
We don't use the F word in my class. That's disrespectful. Foiled. We did what? We distributed. Some of your teachers may have called it foil in the past. We don't call it foil.
I know what you're talking about.
We distribute. That's all we're doing. It's distributing, okay? Now, one thing I'm going to go ahead and quickly show you, because this is going to help you long term, because we're going to use this later. There is something called the area model that helps me distribute. Okay, when we say area, what do we immediately think about? But like, what shape do we usually think about when we think about area?
A square.
A square, thank you. Okay, so I'm going to draw a little square here. And I'm going to put some sides in here. And so the first side is going to have an x plus 3. That's the width of that square. And then the height here is x plus 3. And I'm going to multiply. Just like I distribute here, what is x times x? What's x times 3? What's 3 times x? And what's 3 times 3? And then I have these like terms here that I'm adding. That negative was still up front. See how that maps or matches that perfectly. Okay? Now, first off, I want to say this. Do you have to use the area model? No. But I promise you, we're going to learn something later where that area model is going to be really helpful. So I would recommend it for the idea of distributing. And it also just helps you stay organized. When we do stuff later, we're not just going to have 2 terms by 2 terms. We're going to have 3 times 3 or 3 times 2. So that area model really is helpful in staying organized. I did not know that when I was in high school. I wish I had. So I get this different. That's okay. You'll see me using it though, so be aware of it. All right. One of the things I want to emphasize about this though is, can you have 2 different equations for the same function? Yes. Okay. Very much so. And within quadratics, we actually have 3 different forms of a quadratic equation. This one is known as a factored form. Any guesses why? It's known as the factored form. Hey, what do we do with factors? That's a great question. What do we do with factors, guys? We multiply them. Hey, what's happening right here? They are being factored form. This one is closer to what we call a standard form. ax squared plus bx plus c. Hopefully remember some of those letters. That's known as a standard form. Okay. But at the end of the day, focusing on the idea, they're equivalent because the same inputs are mapping to same outputs, right? Same inputs are mapping to the same outputs. What questions do y'all have about that, by the way? Going once, and twice. And don't forget, until we learn how to actually find those features of the parabola from here, focusing on same inputs to same outputs is fine. Tomorrow we'll start learning about those different forms of a quadratic. B here. Did anybody find anything that went with B? I see a W. Anybody find anything besides a W?
E.
Which one?
E.
E as well? I did have E. Yep, I agree. How do we know that they go together? How could you have figured that out?
I put it into the calculator.
I say, can you graph this on using a calculator? Use your tools strategically, right? One thing I would point out here as well, not just using the graphing calculator strategically, remember the same inputs map to the same outputs. This is the point 1, 4. So what should f of 1 equal here? It should equal 4. Sorry, that's a negative 1. Why don't let me lie me all like that? I'm like looking at this, I'm like, that's not gonna work. So, 1 minus 2 plus 5. 6 minus 2 is 4. So did the same input map to the same output? So if I were to graph all of those inputs and outputs, that would be exactly the same graph. So don't forget, I just grabbed my point, I found my input and output, substituted the input in to see if it gave me the same output. I also had L. Notice there's that negative 1, 4. The same input mapping to the same output. Okay? Alright. That was actually the only one I had. I did not have W with B. So I'll have to find what W was later and look at it. C, when we look at this table and this equation and that graph and this verbal representation, what should we notice? What should jump out about all of these? So what? It's linear. What do we see in every single representation? Repeated addition or constant repeated addition. Plus 2, etc. And I will say this, I'm going to come back to these on Wednesday after we do a demonstrated understanding because I'm rushing, I know that, and some of y'all need time to take notes. I'm trying to cover some things. So, by the way, what form is this one called again? It's factored form, right? They're being what? Those expressions are being, well, they're being multiplied, which we multiply factors. This is known as standard form. Anyone remember what this is from Algebra 1 last year? Does this jog anybody's memory? At least looks familiar. It starts with a V. Vertex form is the last form that we will study. But again, we're going to come back to this, talk about some of these details later. By the way, I wanted you to notice, did I do W yet? No, maybe not. VO and X all went together. Yep. Oh, I did W somewhere. VO and X all went together. What's unique about this one? None of them, they're not a function, right? One input mapping to more than one output. Okay, again, we'll do notes on this on Wednesday. I need you to grab a seat really quickly. Mr. Hobby, where are those demonstrate understandings?
Back here.
I want to go over a couple of details, and you already scanned them to me, right?
Yes.
Okay. And Kelly, don't let me forget to use the test.
Do you still want to record, Mr. Kenny?
Bella, say again?
Do you want to record?
Yes, please. Malia, hold on to him until after Wednesday. Malia, Hope, Xander, Mia. Actually, Mr. Hobby, can you pass out that half? And
Davis. If you want to remember names. Davis.
Leah, Miles, Sarah,
There's Davis.
Peyton, Damien, and Landon,
Brianna.
and someone does not have a name on theirs, so you're not getting yours back. I mean, I'll give it back because it is up. Yeah. All right. Really quickly, guys, listen.
Kelly.
Couple of key details. One,
Drake.
justify why you're saying it's linear or exponential,
Kennedy.
right? Don't use the word it. It is not clear. The graph shows an exponential curve.
Elizabeth.
The graph shows a line. But here's what I need us to look at really quickly. Okay. Be careful with things like this. First off, do not forget, and I would have done this, and a couple of y'all did this very well. Shadidra, is this yours then? Yeah. Okay. Some of y'all did this very well. What I probably would have done at the very beginning of this assessment is written out my equations. Guys, what are the equations? What's the equation for a linear function? There's a whole lot of us that left off x's. If you don't have an x, you don't have a function. There's quite a few of us who left off the equals y. If you don't have equals y or equals f of x, guess what? You don't have a function, because you got to have inputs and outputs. You got to have them both. What's the equation for an exponential? And what I will point out is, if you prefer this, I'm starting at A and I'm repeatedly multiplying by B. Here, I'm starting at B and repeatedly adding M. You can rewrite it if you want. Some of us did that. But right here, this is what I want to point out. I'm going this direction because I go from negatives to positives. So here, it was 16 times F is equal to 8. So F is not 2. What is F? 1/2. Notice, I have labeled, guys, we still have a couple minutes, I want y'all to pick this up. We have a constant factor, here's my y-intercept, and now that I've identified these things and I have my equation, it's super straightforward to say, hey, 2 is my y-intercept. B, my constant factor, is 1/2 raised to the x. Notice that if we write out the equation, label those things, it is super, super straightforward, which none of you have. You're demonstrating understanding, and I'll still thank you. I wanted to borrow this. In a similar way, if I'm looking at number 6, g of x equals 6 times 2/3 to the x, remember, the same inputs map to the same outputs. What I would have probably done is start with a table. I always like starting with tables. The input of 0 gives me what output? Anyone know? Gives me a 6. Isn't that my y-intercept right here? And if you had just checked it, and just substituted that 0 in and shown that evidence and typed that into the calculator, you get a 6. If you type in a 1, you get 6 times 2/3 to the first, that gives you a 4. And you do 2 and you get 8/3 because it's multiplying by 2/3. And then you have some points to graph. Please study the feedback that I've given you. I will do some work through on these type of problems and post it on YouTube. So look for that. We're going to have these type of problems on your demonstrated understanding on Wednesday, where you have to